Hello. Everything seem okay?
Yeah.
I somehow ended up in a different meeting. I don't know if I accidentally clicked on the wrong button, but I I I was in a meeting by myself for until I realized that something was really wrong. Um, yeah, I don't know if I clicked on the wrong button or if something went flaky when I had to authenticate with Boiler Key, but I ended up in a meeting by myself. So I had to get out of it and then get back in. So I'm not sure what went wrong there. Okay, but everything seems okay now, right? Okay. Okay. Let's see. Okay, today we're going to keep talking about virtual memory. I mean, it's going to take us for the rest of the semester to talk about virtual memory. There's a reading assignment for the next section. Okay. Oh yeah, the section we're doing today we're going to do well, this chapter and this chapter here talk about a preliminary version of virtual memory. That's kind of something to help us get to the real version of virtual memory. So the thing here is called base and bounds, and the thing here is called segmentation. And we're trying to build up to the real thing, which is called paged virtual memory. But that takes a lot of it takes some setting up to get there. So we're looking at these old-fashioned systems, but they're not old-fashioned in the sense that they're old-fashioned in the sense they're not being used, but they're not old-fashioned in the sense that their ideas are still very relevant. The ideas are real useful. They're just not actually used verbatim anymore. The ideas become part of paged virtual memory. Okay, so and then I have here a link to a homework assignment, but it's not ready yet. Okay, so it's not there yet. Okay, and hopefully it'll be there in a day or two. Okay, so let's start talking about this mechanism, address translation. Now, he doesn't draw any pictures in his book. Well, I mean, not much. He draws only the picture of what he thinks of as virtual memory space. But what I think is maybe more useful is to think in terms of what the hardware looks like. Now, he does keep pointing out that he's talking about hardware-based virtual memory, but he never gives you a visual sense of what he means by the hardware. So we're going to keep working with these pictures that we've been working with and trying to go back and forth between his description and a few pictures. So like the key picture is this one from here. I'm going to just download this one and want to add to it today. Okay, I'm going to start with this picture. The key is this box right here. He mentions that box in his discussion, but never draws a picture of it. This box, I think, if you think of the CPU over here and the memory over here and this box in between them, the memory management unit, I think that helps a lot in terms of understanding what's going on. Physical memory over here, the physical CPU over here, this unit between them, and then you're trying to create the virtual memory abstraction. Okay, very much like what we did before, where essentially the timer and the mode bit created the virtual CPU abstraction. Now the memory management unit is going to create the virtual memory abstraction. So I think it helps to have this picture to see that the abstraction's coming from something physical in the computer. The virtual CPU abstraction comes from the timer interrupt and the mode bit. Okay. The virtual memory abstraction comes from this thing called the memory management unit. Okay. Now, the important part of this picture, the details matter. Okay. The CPU has a size of its registers. That's this letter N here. That's how many bits are in this CPU. This means that this is N bits coming out of these registers going over to here. N bits are used to look up memory addresses. Okay, so if you had a super simple computer, you would just have this, you would just, if there were 16 bits here, you'd have 2 to the 16 memory locations over here. And every word here would access one word over here. But modern computers don't work that way. There's 64 bits over here. There can't be 2 to the 64 memory addresses over here. That would be way too many. The planet couldn't hold that. Okay. So the CPU talks in what we call the virtual addresses, VA for virtual addresses. So if there's 32 bits in this register, N is 32 bits. If there's 64 bits in this register, N is 64 bits. So that's how many addresses the CPU thinks it's talking to. The CPU thinks it's talking to virtual memory. See, virtual memory goes from 0 to 2 to the N. So if this is a 32-bit computer, virtual memory addresses go from 0 to 2 to the 32, which is 4 billion. If this is a 64-bit computer, addresses go from 0 to 2 to the 64, which we said the other day, that's 16 exabytes. Okay, so that's a lot of memory. Okay, but that's what virtual memory is. And every process, the CPU sees this when the CPU is in user mode, that's what the CPU sees. So each process thinks it has, in the case of Windows, each process thinks it has 16 exabytes of memory. It thinks it does. The CPU, for all it knows, can access any one of those to the 64 memory locations. Okay, we'll see what that turns into. But from the point of view of the CPU, it could access any one of those 2 to the 64 memory locations. On the other hand, over here is the real memory. The memory management unit will turn the virtual addresses into physical addresses. It does address translation, which is the name of this chapter. Address translation. So the thing he's saying here is this box here. Yeah, that's why I wish he would have the picture, because the very name of the chapter is exactly what that box is all about. It's the memory, it's the address, it is the address translator. It's the thing that translates the virtual addresses coming in into physical addresses coming out. This is your actual memory in your computer. If you have 4 gigabytes of memory, then N would be 32. If you have 8 gigabytes of memory, then N would be 33. If you have 16 gigabytes of memory, 16 gigabytes would be 32 to the 34, so N would be 34. There'd be 34 bits of address. Now, every address is 1 byte. Okay, see these, remember, memory is an array of bytes. So if you have an int takes up 4 of these bytes, not one of them. And that means if you have an int at memory location 100, the next int's not at 101, the next int's at 104. And you have to keep, it's kind of a weird, flaky, it's kind of an odd situation. The inherent size of memory should be either 32 or 64 bits, but it's been decided it would be 8 bits. So 2 variables next to each other aren't going to be at consecutive memory addresses. You're not going to have a variable at 100 and 101. The variables will be at 100 and 104. Then the next variable will be at 108, because you need at least 4 bytes to hold a variable. If it's an int, it needs 4 bytes. If it's a double, it needs 16 bytes. Or no, it needs 8 bytes for us. It needs 8 bytes to hold a float. A double, I'm sorry. Ints and floats are 4 bytes, and doubles are 8 bytes. Now, characters are 1 byte. That's kind of maybe what motivates this, but not really. But if you have 2 variables that are both byte characters, which aren't very useful variables, but they could be next to each other. Okay, so the addresses address these bytes. Okay, but the key is that there's only, say, 4 gigabytes over here. Okay, virtual space is 16 exabytes. Physical memory space is 4 gigabytes. So this is billions and billions of times bigger than what the physical memory is. Okay, the CPU doesn't know about this. The CPU thinks it's talking to this in user mode. When the CPU is in kernel mode, it essentially bypasses the memory management unit. Yeah, if you're in kernel mode, these addresses go straight over to here. They kind of bypass the memory management. They actually technically don't bypass the memory management unit, but the memory management unit is going to be set up in a way where when you're in kernel mode, the PC address, the program counter goes straight over to memory. That way, the CPU can see all of physical memory. Okay. Now, in physical memory, actually, I downloaded this picture. I want to switch to like drawing a little bit on it. So there. like before, we in physical memory is going to be a bunch of different things. So for example, the operating system might be this region of physical memory. Okay, so that's maybe where the operating system is. And then like we did before, you might think of like color coded a little bit to make it easier to think. There's some process, whoops. There's multiple processes sitting in virtual memory. So maybe this is process 1 and this is process 2, and then down here is a process 3. So there's, say, 3 processes sitting in memory. So over here is the operating system. Okay, this might be process P0 here. Process P1 here and process P2 here. So we got 3 processes and the operating system in memory. And remember, the whole crux, the really important issue is that when you're in user mode and the CPU is executing in one of these processes, if it's executing in here, it shouldn't be able to see anything in here, here, or here. When the CPU is in user mode and it is working on that process, it shouldn't be able to even see any of these other processes. What we want to talk about today is now a specific way that we can keep the CPU from seeing outside of what its piece of physical memory is. So this memory belongs to one process, this belongs to another process, this belongs to another process, and the operating system's up here. When you're in kernel mode, the CPU can see all memory. It has to, because that's how it wrote that program in. The CPU loaded that program into those bytes, and it did it by copying from the hard drive to that region of memory. So it somewhere in this picture would be the hard drive where the EXE files are stored. The EXE files get copied into memory by the CPU. So the CPU had to be able to write that data. So that's done in kernel mode. Now, in user mode, we want to start talking about a specific way that the CPU can't see outside of that range and how it creates essentially a virtual memory space. Okay. So what we're going to do is in the memory management unit, there's going to be 2 registers. Okay. There's going to be 2 registers in the memory management unit. They're called base and bounds. Okay, so there's going to be 2 registers in there. The upper one is called the base register, and the lower one is called the bounds register. Okay, and then when you load, for example, process P0, what this register it holds the address of that top of this box, and this register holds the address of the bottom of that box. That's all it is. It's as simple as that. The base register is the base of your physical memory space, and the bounds register is the end of your physical memory space. So this process, when it's running, when this process here, P0 is running, the value in the base register points to there. So I can maybe just draw this thing. When you're running this process here, this one will point to there, and this one will point to there. Okay, so I'm thinking of these as pointers. These double arrows are bits. See that? This is data. When this CPU wants to send data to a memory location, it writes n bits of data. This is an address. The address bus chooses a location. The data bus puts data in a location. Okay, so it's like, think of an array. When you write to an array, you need to know where in the array you are. That's this bus. Then you need to know what you're going to put in the array or what you read out of the array. That's this bus. Address and data. All CPUs are divided this way. Now notice that the data bus is the width of these registers. If this is working with 32-bit integers, it needs to write 32 bits. The data is the width of the registers. The address bus is what gets switched. The CPU thinks that data and addresses are always the same. If data is 64 bits wide, addresses are 64 bits wide. That's one of the cornerstones of modern CPUs is the data size and address size are the same to the CPU, but not to over here. If an integer is 32 bits, then the data bus is if data is 64 bits wide, the data bus is 64 bits, but addresses don't have to be 64 bits wide. They don't have to be 2 to the 64 memory locations. So we have an address bus and a data bus. And you think, think of memory as an array. It is almost everybody, if you look in an architecture book, they always describe memory as an array of bytes. An array has the index, that's this column over here, and then the entry in the array. The address bus chooses the index, and then the data bus writes the data into that index. Okay, so the data bus is the width of the data. In our case, that's the size of your registers. In this case, it'd be 64. The CPU issues addresses that are 64 bits wide, but the memory management unit has to trim them down essentially to being reasonable. Okay, these I'm thinking of as pointers. That memory, look, that register holds that address, and that register holds that address. So these are just pointers. So now what happens is when a virtual address goes in here, it's compared to the base and bounds register. Well, no, that's not saying. When a virtual address comes in here, well, let's see, let's backtrack a little bit. Let's look at an example from the textbook. He kind of explains this part here. He has I'll show you where he explains this in the textbook of what he wants to do. In the textbook, he describes what we're trying to do with a little bit of code. Okay, in this process, we imagine that there's this code. He's got he wrote it in C here, but it's really an assembly language. So here's the assembly language that represents that C. Okay, all right. So there's a little bit of code in here. Load a variable with the value 3000, then add 3 to that variable. So go out, get the value 3000, put it in the variable x. Okay, then take the 3000, add 3 to it, and store it in x. Okay, all right. Then over here in machine code, this would translate into this. A move is put data somewhere. Okay, so he's going to here to get the data. That's where the 3000 is going to be, and he's going to be putting it in here. Okay, so move 3000 into here. Okay, then add 3 to, oh, actually, I read it backwards. This is where he's fetching the data from. Fetch the data from here, put it in here. So fetch the 3000 from somewhere. The 3000's in here. It's in that memory location. So it's the 3000 is somewhere. Put it in here. Okay. Then add 3 to what's that 3000. Then take the 3000, put it back where it came from. Okay. So actually, this, you can think of this as the x. Okay. Okay. So actually, oh, this instruction, this code here is just this one line of code here. Yeah, those 3 instructions are that line of code, not the 2 lines of code. Read x, add 3 to it, store back in x. Here's x. Read it into a register. So over here, this picture, x would be down here. The first thing you have to do is load x into a register where the CPU can work with it. So you're going to go get x out of memory, move it in that direction on the data bus into one of the registers. So you would move x into a register called EAX. Then you add 3 to that register. Okay, that's the right-hand side. Well, these 2 instructions do the right-hand side. Read x, add 3. So this reads x, adds 3 to it. Then you have to put the result back where x was. So then the result gets put back where it started from. So that would take the result in the register and send it back to the where X is. So X is a location down here, and he wants to get X into a register, add 3 to the register, then send it back over to here. Okay. Now the question is, how do you treat this address of X? Okay. Should the what address should the CPU think it's using when it accesses X? Now think from the point of view of the compiler. When the compiler said where X is, the compiler doesn't know if your process is going to end up here in memory or down here in memory or down here in memory. So the compiler can't put the address of X into the instruction because the compiler doesn't even know where the program is going to get loaded. These programs could get loaded anywhere in physical memory. So when the compiler created this code, it didn't know where X is going to be. Now, what it does know is that it knows how far X is away from the top. So it could say, well, X is a certain distance from this base. So that's how the compiler will imagine it. The compiler will say, well, there's a base here that we're going to call 0. So we'll think of that base as a little local 0 address. Okay. So the base is a 0, and then X down here is a certain distance from 0. So the X variable, which may be the X variable, maybe we think of it as over here. Here's the X variable. That's confusing because that looks like that's X is the variable. The variable should be outside that box because what's in here is the value of X. So I can squeeze X, just put it right here. That isn't visible. Okay, just put it outside here. See, X is a variable, so it's not what's inside the box. So the variable is down here, but it's a certain distance away from the base. Okay, so the compiler, maybe X has address, say, I think he uses a value here. See, 3000. Here's where his X is. Well, actually, this is the see the 3000 value. So X is this address here. So X would be 15,000. See, there's the value of X. So in our case, if I did it in his way, this would be the number 3000 to start with. That's in X. Okay. In his picture, there's 3000. It's at that memory location. Okay. That memory location is measured from 0. Okay. So see this picture here is this blue box over here. That's the virtual memory. Well, that's the memory space that here I've drawn it sitting in physical memory. Here he's drawn it as if it was a virtual memory space. So he's drawn it as a virtual memory space. I've drawn it as actually sitting inside physical memory. Okay, so this is the program running in memory. But here you think of it as its virtual space, how the CPU thinks it's seeing it. But it's really sitting in physical memory like this. Okay, it's sitting at some address in physical memory. The actual address of X is not going to be, say, 15. In his case, he used 15,000. So you're 15,000 bytes away from that top. Okay, but that's 15,000 bytes away from the top. That's not what this actual address is. Okay. Now the CPU can't be fed that actual address because this program needs to be able to be loaded anywhere. So what the CPU, what's actually in the code is that offset from here down to here. Okay. The virtual address is what's inside the CPU. The CPU knows when the CPU wants to access that X, the CPU is told by the compiler that distance from here to here, which is the virtual address of the variable X. So the CPU has the virtual address. But the memory management unit has to translate that to the physical address. That's really going to be whatever. Now notice that the physical address is this base register plus that virtual address. Okay, So the memory management unit, what it does in base and bounds is it takes in virtual addresses, which are really offsets from this base address, and it adds the virtual address to the base address to give you the physical address. Okay, so let's see. You can write that as a formula. Actually, oh, let me show you. Um, I have this little zip file that's got some pictures in it that from other textbooks that show they're pictures that are kind of in between what we're doing and what the textbooks don't doing. So there's some more pictures. Okay, here's the picture of the algebra that is going on here. Let me squeeze this in. Okay. A virtual address comes out of the CPU. You can kind of get all these. Okay. Ah. A virtual address comes out of the CPU. The virtual address is you take the virtual address, which is see, the virtual address is the program counter, for example. It goes over here into the memory management unit. The virtual address is added to the base, okay? And then the result is the physical address. See, virtual address goes in, gets added to the base, and you get physical address out. So you see this picture in a lot of textbooks. Our textbook doesn't show this picture, but this picture, it's on Wikipedia. It's shown. I'm not sure why our book chose not to like draw this little picture. I think it helps a lot. And I can't clutter up this picture too much over on the right, but this is this combined with this shows kind of gives you starts getting you the sense of what's going on. The physical addresses come into the memory management unit. Memory management does this calculation. The virtual addresses are actually offsets from the top here. The base register is the actual physical address of that top. The virtual addresses are offsets from that top. So down here, the virtual memory space starts at 0. So virtual addresses can be thought as offsets from the top. So an address of 17 is 17 units down this way. But what we do now is we think of 0 as actually being the top of this region. So 0 is here for this process, 0 is here for this process, 0 is here for this process. But essentially, this box is virtual memory. And this box is virtual memory. Because if you think of it in terms of offsets, you start from here and go down. But this, so the virtual memory is usually it's thought of as sitting over here by itself. That's the right way to think about it. But you can think of it as being embedded over here. Then the virtual addresses are actually the offsets from the top. The base register of the memory management unit is what puts makes 0 the right place in physical memory. If the virtual address 0 comes in here, it's added to the base register. 0 plus base gives you the base. There's the physical address that's the equivalent of address 0, of virtual address 0. Now, what about the bounds register? The virtual address can't be larger than this. See, this one points to where your limit is. If he could issue an arbitrarily large virtual address, he could just take the 0 and add an offset down into here. Now, he would need negative numbers to move in this other direction, but there are no negative addresses. See, when you add virtual address to base, if you added negative numbers, you could move that way, but there are no negative virtual addresses. But if the virtual address was large enough, you could go past this end here. So what the memory management unit does is essentially does this in the actual CPU does this in parallel. At the same time it's doing this addition, it's checking this inequality. If the virtual address is larger than the bounds register, if the address that comes in here is larger than this, throw an error. Okay, so two things happen with this virtual address. The virtual address comes in here. It is added to the base address, and it is checked against the bounds address. So that's shown here as happening in parallel. the virtual address is checked against the bounds register, and the virtual address is added to the base register. If this is not an error, then the physical address goes out, and the physical address goes to the variable here, x. Okay. This, now we actually have a concrete way to say that this process can't see outside of its little blue box when it's in user mode, because every virtual address that the CPU spits out, every virtual address has to be filtered through the memory management unit. The memory management unit does this calculation. If the virtual address is too big, the bounds register will stop it. And then the virtual address, if it's not too big, will be translated into the right location in the virtual memory space. So this space here is this. Now remember, this one starts at 0 and goes up to 2 to the 64, which means that the CPU essentially just seeing a tiny, tiny sliver of its virtual address space. Yeah. So the CPU is only seeing, I can't see my mouse. The CPU is only seeing a tiny sliver of its virtual address space. It sees from 0 up to the bound. The CPU could issue, now remember, this is an old-fashioned CPU. Modern CPUs don't quite do it this way. We'll see how this idea helps us understand what the modern ones do. But if we were really imagining this as a 64-bit CPU, these would be virtual address spaces of a couple gigabytes. But this would be, I'm sorry, these would be physical address, these would be physical processes of, say, a gigabyte of memory, but then this virtual address space would be 16 exabytes. So this, the potential virtual address space could extend from, see how the mouse just disappears? See, there's the mouse pointer, real visible. Then when it moves into here, it just disappears. I'm not sure why it's doing that.
It looks like it's changing into the thing for selecting a part of a text.
Yeah, so maybe I'm in the wrong. Can I like turn it into a different pointer? Yeah, probably. So what I need to do is turn it into one of these other pointers. That's a little bit better. No, that's bad. That's bad. Okay, that's a little bit more visible. Yeah, I choose a different thingy up here, and it gives me a little bit better mouse pointer. It's not as good as that one, but it's a little bit better than what it was. Okay, so virtual addresses could extend 16 terabytes this downwards from here, but there, you don't have that much physical memory. So it's the compiler decides how much physical memory you need when your program runs. If you wrote a small program, you're not given much physical memory to run your program in. If you wrote a really large program, the compiler would realize you need a larger physical memory. So this is a small program that doesn't, its base points to here, and its bounds just says it doesn't need that much memory space. This one, the base would be pointing to here, and then the bounds would say it doesn't need that much memory space. The compiler chooses what the bound is. The operating system chooses what the base is. When this program is loaded into memory, it's copied from an EXE file. The EXE file will tell the operating system how big that program is. So essentially the bounds is the size of the EXE file. Essentially the bound is the size of the EXE file. The operating system chooses the base. The operating system chooses where to load the process. So if another process wants to run and it's small, the operating system could put it right there, or it could put it right there. So when the operating system loads the process, the operating system chooses what the base register should be for that process. But the bound register comes out of the size of the process. So that's actually, essentially, it more or less is going to be the size of, well, it actually won't be the size of the EXE file, because as we see in this picture, if we can go back to his picture, your program is not just your EXE file. Your program is the EXE file, the code, and the heap, and the stack. So when your program is loaded into memory, from our point of view, maybe the code is up here. That's the size of the EXE file. And then the operating system decides how much heap and stack space you'll be given. So this box here would be the code at the top, then the stack, then the heap, or the other way around, the code at the top, then the heap, then the stack at the bottom. Okay, so that map, that memory map there is sitting inside of here. Okay, so the size of the exe file would be the size, so the bound is going to be how big is your exe file plus how much stack and heap space the operating system wants to give you. Then it determines what the bound would be. So the bound is a combination of how big the program is as determined by the compiler and how big a stack and a heap the operating system gives the program. And the operating system chooses the base register because that's where it loaded it in memory. Okay. Now, when you do a context switch from one process to another, part of the context switch is, in addition to changing all the register values of the CPU, you change the register values of the memory management unit. To some extent, you can think of the memory management unit as two new registers in the CPU. Some books kind of teach it that way. They just teach it as these two registers are two hidden registers inside the CPU, but that kind of obscures what they're really there for. They really, I mean, they really sit sort of in between the CPU and memory. And if you go back into the 80s, Intel actually sold the memory management unit as a separate chip. When you bought a CPU from Intel back in the 80s, if you didn't have much money, you bought a CPU and physical memory, and you didn't have a memory management unit. You didn't have virtual memory. And if you had more money, you could buy the memory management unit separately. It was actually literally a separate chip that you bought in addition to the CPU. So then you could have a fancier computer with virtual memory. Long time ago, the memory management unit became part of the CPU. The memory is not part of the CPU. You buy the memory separately, and it's separate on this motherboard. But on a modern computer, starting somewhere in the 80s, the memory management unit just became part of the CPU. But there was a short time when it was an add-on. You actually paid extra for the memory management unit. Same with the floating point unit. You paid extra for the floating point unit, and you paid extra for the memory management unit. I think it's still better to be thought of as a separate unit. Think of it as separate from the CPU. It sits between the CPU and the physical memory. It's on the die with the CPU, and it's part of essentially the CPU in a modern system, but logically it sits between them. And it takes the virtual addresses coming out of the CPU, checks them against the base and bounds register, and issues physical addresses out here. And now we have a concrete way to have virtual memory separated from physical memory. This process thinks it's running in this virtual memory space. The CPU thinks it's running in there. As long as it keeps its addresses within the range that is the bound, any address that goes through here will be translated to an appropriate physical address. So if we go back to this variable here, the variable x in the program is thought of as how far it is away from this base. That's what the CPU thinks it is. The CPU just thinks x is a certain distance from the base. But the actual address of x, the CPU never sees it. The actual address of x is going to be the base plus the offset of x. And that actual address of x depends on where this program is loaded in memory. Now, for example, suppose somebody wants to run a medium-sized program at this point. Well, there's a small amount of free memory there, small amount of free memory there, small amount of free memory there, small amount of free memory there. There might be enough memory to run a medium-sized program, but it's all in fragments. So at this point, the operating system can defragmentate memory, which is a really important concept. The operating system can say, oh, I need to run this process that would fit if I made room for it. What I can do is I can move him up, then move him up, then move him up. And then if I move them all up, I make enough free memory at the bottom to run this new process. That's called defragmentating. That's real easy to do in this system. The variable x, he's really thought of as an offset from here. The actual value of the address of x doesn't really matter much because the CPU, from this point of view, it just thinks of x as a certain distance from 0. If I take this blue box and slide it up, the way I slide it up is to change the base register. So I copy all this data, just copy all the data up, change the address in the base register to be up here, and then x is still a certain distance from the base. So I can relocate my programs for free, essentially. It's not quite free. I have to spend the time to move them. And later on, we'll see that that even is too much time. The modern memory system doesn't need to ever move programs. This was the big problem with this system. One of the problems with this system is that when memory was fragmented and you wanted to make room, you made room by shifting everybody up in memory or shifting them down, however you want to do it. But you had to shift everybody in memory. That actually takes the CPU quite a bit of time. Shifting is doable. You just copy and then update the base registers. The CPU doesn't even need to know that this thing is not sitting in the same place in virtual memory, in physical memory. When this guy moves in physical memory, doesn't matter. X is still a certain distance away from the base, and that's all the program knows. When the CPU is executing the program, to go back to the book here, that's what he's trying to make the point is, in this code, which is what the CPU is executing, this guy is really, see that thing here? That's that base 0, and this is the offset from it. So now we can go back and say, this is the virtual address that's based off of that. Okay, so this register here is holding the address of X. Okay, and here it's being said that it's actually based on 0. Okay, so the X is a certain offset from the base. And when you, that's the actual, from the point of view of the CPU, the address of X is how far away he is from the base. So if you move the whole blue box up, doesn't really change where X is. Of course, it changes where X is, X moves. But the CPU isn't using the actual address of X. It's using essentially this relative virtual address of X. It's thinking of X as being in the virtual memory space. So X is somewhere down here in the virtual memory space, and it's really got an address that's an offset from 0. Okay, so it's simple at the same time as complicated. Okay, once you're used to this, it feels real simple to you. When you're reading this and seeing it explained by me, it looks like there's a big mess of things going on. I've got one explanation over here. He's got one explanation over here. It's in terms of code, and he doesn't really, he never draws a picture of a CPU. Yeah, he mentions the memory management unit. Where was it? Oh, page 7. Let's see. Yeah, it's not till page 7 that he even mentions the memory management unit. And he points out that that's the thing doing the address translation. I think he should make it more clear what the memory management unit is really important. So he emphasizes this idea of the code and the virtual memory space. Okay, so he emphasizes the virtual memory space and the code sitting in it. And he's a little bit kind of not clear on exactly what the memory management unit is doing. Okay, this other picture I think makes the memory management unit much clearer, especially when you combine it with this picture, which is what the memory management is doing. There's the algorithm. That's the code. That's the algorithm that's built into the memory management unit. Its job is to take the virtual address, do two things simultaneously. Take the virtual address, make sure it doesn't exceed the bounds. If it does, throw an error. Oh, yeah, see this, see, there's this interrupt coming from the timer into the CPU. And in this picture, I put another interrupt. This is actually how it would work. If the bounds in this picture, error really means interrupt. Okay, and here I'm trying to be real, give you a sense of what's really in this computer. When the memory management unit detects this error, it raises that interrupt. Okay, and that does the same thing that any other interrupt does. It forces the CPU back into kernel mode in the operating system, but it'll force the CPU into the kernel mode in the operating system in the memory error handler. Okay, so if this error is thrown, it's an interrupt into the CPU, which by now we know what interrupts do. They throw you into the operating system in kernel mode, but you're thrown into a specific part of the operating system. This interrupt throws you into the part that handles memory errors. This interrupt throws you into the scheduler. When this interrupt fires, you're thrown into the scheduler to decide who to run next. If I put the hard drive back in this picture, its interrupt throws you into the device handler of the hard drive. Every interrupt throws the CPU in kernel mode into the operating system code in a specific interrupt handler. Okay, so error here, now here, they're being kind of vague. What do they mean by error? Well, this picture makes it more concrete. Error means the memory management unit interrupts the CPU. Notice that interrupt is just one bit of information, just one bit that says error. Okay, so that's a 1-bit piece of information going back this way. Okay, so the memory management unit does this. Virtual addresses come in. Virtual addresses are now really thought of as offsets from 0. That's all this virtual address space is down here, offsets from 0. The virtual addresses come in. The offset is added to the base. So the virtual address is added to the base to get the physical address. But at the same time, it's being checked that it's not going past the bound. If it's going past the bound, the virtual address never really makes it out of here because the CPU is diverted back into the operating system by the interrupt over here. Okay, relocation is easy. If you need to make room for another process, if you need to defragmentate memory, you slide everybody up. That's time consuming, but it's not hard. You just copy him up, copy him up, copy him up. Then when you copy him up, you update his base register. Now, his base, if you're running this process here, his base register is in the memory management unit. Real quick question. If you're running him and you move him up, where's his base register? So you move him up, you have to change his base register. That's right here. Where's his base register? Can't be here because this base register is his. Anybody think where would his base register be? When a process is not the actually running process, when it's in the block state or the waiting state, where is all the information about that process?
In the program counter?
No, the program counter is part of the CPU. Okay. Where do we store the information about processes that are waiting?
It's the process control block.
Yeah, the process control block. This was our other picture from before. Yeah, I could have been updating even this picture here. See, it's got the memory management unit. See, notice how we're kind of more or less mimicking very similar pictures here. Okay. But here we were emphasizing the processes. Ugh. The process control block holds all these registers. So this process has its process control block. This process has its process control block. When you're running this process, the data from this process control block is actually in the CPU. When it's time to switch from him to him, you take all his data, move it into the process control block, take this process control block, move it into the CPU. Now you're switching to this guy. Now we have 2 new pieces of information to add the process control block. The base and bounds register in the memory management unit are part of the process control block. So just like all the other registers in the CPU, when you switch from one process to another, everything that's in the CPU goes into the process control block, and then everything from the process control block goes into the CPU for the context switch. So in this picture over here, when you slide him up, you'd update his base register. Then when you slide him up to make room for somebody else, you'd update his base register in his memory management unit, in the process control block. And when you move him, you'd update his base register in his process control block, because only one of the processes is actually running. Only one of the processes actually has its base register in the memory management unit. The others have their base registers in their process control blocks because they're not currently running. Okay, we have to, to understand this, you have to keep all this stuff in your mind at the same time. None of this goes away. Virtual memory and processes are not separate topics. We linearize it by teaching processes first and virtual memory later, because it would just be too much of a burden to teach it all at once. But it isn't separate topics. It's one topic. It's how does a CPU implement an operating system? And it's part of, well, what you want to do is, if you want to understand this and be able to use this information when when you write real code, this information is real valuable for understanding, especially in these days when everything's running on a cloud on virtual CPUs, and you're trying to figure out what's really going on. This stuff actually helps this stuff is underlying a lot of what modern programmers have to deal with. They have to understand what their code means when it's running on a cloud. Understanding this stuff here helps. Okay, but it isn't one topic is processes and one topic is virtual memory. We just teach it that way. They are intertwined together. This picture, which we emphasize for processes, and this one we're emphasizing for virtual memory, still the same picture. We're just really adding to this picture over here. So in this picture, there's still the process control blocks. They're still part of the picture. And the process control block now includes the base and bounds register. Okay, so to defragmentate memory, copy him, update his base register, copy him, update his base register in the process control block, copy him, update his base register in the process control block, and now you got enough free space down here to load with another process. Okay, so one important thing that the base and bound register do is they make it possible to move processes around and what we call defragmentate memory, okay, which is important. Memory will always get fragmented because as processes come and go, you get holes in memory. If you've got your memory full of processes, as soon as one dies, now you have a hole. And when another one dies, they're not going to die next to each other. So now you have two holes. The two holes are not next to each other, but combined together, they might be enough room to run a new process. To get two holes into one, to get that hole and that hole coalesced, you have to take that process and move it. If you take that process and move it up to there, then those two holes coalesce below this one. Okay, that might be enough room. You may not need to move all the processes. You may need to move just one of them. That's the job of the operating system. When it's time to make room for a new process, the operating system, well, in the old days when they did this, the operating system would have to kind of figure out, who do I move to make room for a new process? Windows never moves processes in memory because we don't use base and bounds anymore. So moving processes in memory is such a time-consuming thing to do that the modern paging system eliminates the need to ever move things in memory. Okay, so we actually don't move things around in memory in a modern system anymore. To make room for a new process, we don't slide him up. We don't have to do that anymore. So as we keep on going through this, we'll see how we can get around having to slide things around in memory to defragmentate memory. It's what they came up with was a tremendously clever idea. The page virtual memory system idea, it's more complicated than this is, but it really solves this sliding around problem in a beautiful way. It's just a really clever, some engineers back in the 70s came up with a really great idea to avoid having to slide programs around in memory. And we're going to see, it also solves some other problems. There's going to be several problems we eventually want to solve, okay, that this base and bounds doesn't. Okay, now here's an example of here's a problem that we want to solve that base and bounds doesn't solve, but we will solve eventually. Everybody writes code using the C library. So for example, printf, scanf, open file, close file. You have all this code that makes up the standard library that's part of your program. So if over here, let me think of it this way. In my program, there's a chunk of memory. Oh, that's a really lousy color. No, let's see, what's the color that'll show up? Okay, that shows up. That code there, think of that as the C library. But that library's in this guy's code too. And that library's in this guy's code too. Because everybody's using printf. So there's a copy of printf here. There's a copy of printf here. There's a copy of printf here. Okay. Now, right now in my computer, if I go here to Task Manager and you look at details, I'm running hundreds of processes. That actually means that I have hundreds of copies of the C library functions in memory, hundreds of them, maybe even thousands of them. The printf function, every one of these is going to be written in C. Almost all of these things are actually written in C. And the basic library is just going to be copied over and over again in these. So in a sense, this little purple box is going to be here, here, here. That wastes a lot of memory. Why can't there be one copy of printf? Printf is something you read only. It's code. You read the code for printf. So why can't there be a copy of printf, say, just sitting right here that everybody can share? Okay. Now, there's no way we can do that in this system. So what I want to do is I'm going to call that a shared printf. Actually, I'll say shared C lib, the C library. Okay. In computer science, we don't say library, we say lib. Okay. So the C lib. Okay. Why can't I have the C lib in memory once and tell him to somehow, when you need to execute printf, there's printf. When you need to execute printf, there's printf. Well, Windows actually literally does that. All these processes that I show here, they actually don't, they all share a copy of printf. They share a copy of the C library. In a later lecture, we'll see how that's done. That's what you may have heard of DLLs. Go back to our favorite location in the hard drive, which is where Windows sits. We go to the Windows System 32 folder. Remember, this 5,000 files worth of stuff is the operating system. Okay. See how there are hundreds and hundreds and hundreds of files called DLL. DLLs are shared in Windows. They're called DLL, which stands for Dynamic Link Library. In Windows, they're called SOs, for shared objects. They are essentially the thing that gives us this shared library. Okay, in Windows, they're called DLLs. They sit in memory as shareable things. They're not EXE files. EXE files are these programs. EXE files are programs. DLLs are shareable pieces of code. And the C runtime, the C library, see if I can find it. See, I'm trying to remember. No, let's see. It's no, I'm forgetting what they call it. Oh, here it is. See, MSV. See, these things they all have names like MSVC, MSVC. Okay. If you right click, properties, details. See that name? IO streams DLL. That's part of the C library. It's the IO streams part of the C library. Okay, now another one. These are, the MS stands for Microsoft, V stands for Visual Studio, and then these are part of the C library. So Microsoft they wrote their version of the C library for Visual Studio. So it's Microsoft, MS is Microsoft, V for Visual Studio, then CR for C runtime library. C runtime library. See, printf should only be in memory one time. There shouldn't be 1,000 printfs copied in memory because that's really wasteful of memory. So Microsoft writes printf and puts it in this DLL, and then that DLL gets put into memory once, And then there's a mechanism in a modern virtual memory system for everybody to share that DLL. But you cannot do that with base and bounds. This was one of the big problems that base and bounds can't solve. Okay, so that's a problem that base and bounds can't solve. In base and bound system, you have to have a printf in everybody's memory space. You have to put printf in here and put printf in here and put printf in here. You have to basically make copies of it. You can't have a shared printf. Okay, and the modern virtual memory system does do that. This DLL is going to get loaded into memory, physical memory, one time, and then every program that needs to share it will somehow have a way of sharing it. And we'll see how eventually, as we go through the memory management chapter, we'll see how that would work. So one of the problems that we want to solve is the fragmentation problem. Now, base and bounds helps us solve the fragmentation problem. Not in an elegant way. We solve the fragmentation problem by copying. We solve the fragmentation problem by sliding programs up in memory to make room for to coalesce the free areas. By sliding programs around, we can coalesce the free areas into bigger free areas. So, and that's easy to do because we just update the base registers. It's time consuming, but easy. Okay, so base and bounds kind of solves the defragmentation problem, but it doesn't solve the sharing problem. It doesn't let programs share memory. And that turns out to be really important because otherwise there's just way too much duplicated code in memory, and it would just waste memory. It can waste a massive amount of memory to have essentially the whole C library being duplicated over and over and over again in every process. The C library is not that small. Actually, this copy is very small, so only 1 megabyte. You know, it's not quite 1 megabyte. But there's a whole, the C library is actually more than, you notice that there's a whole bunch of these. There's different pieces to the C library. So all of these together form different pieces of the C library. Okay, I don't even remember which one holds printf. You can look them up. On my computer, I can open one of these. I have a special program on my computer that's not, it's part of Windows, but you have to add it on to Windows separately. It's called this dependency walker. It lets me do things like open DLLs and see what's actually inside of them. It takes a little while for it to open up because it's analyzing the DLL. Boy, it's taking a long time for it to open it.
Is it supposed to say not responding?
Yeah, until it opens it. Usually it'll say not responding while it's analyzing the DLL. Boy, it's taking a long time. Let me just kill it and try it again, because that is taking way longer than it should. Let me try picking, let me pick a different one. That's kind of weird. I don't know if I need to reboot my computer. Normally it takes a while for Dependency Walker to analyze one of the DLLs, but then after about 30 seconds, it shows you all the information. And it'll tell me what functions are in that DLL that are being shared. Well, quit that. I'm not sure what's going on. Probably maybe I just need to reboot my computer. Sometimes weird things like that just come from, yeah, if I reboot the computer, it stops doing something weird like that. Let me just randomly pick another DLL. Don't know. Let it just go. Let it go off on its own. Just let it sit there and work. Maybe it'll pop up eventually. Okay, so That's a problem that we can't solve yet. How will we share, how can we share physical memory between two processes so that we don't have to have duplicated code sitting in memory place after place after place? Okay. Now, here's another problem that comes up. Suppose a program, here's a real good example. I use the TextPad editor. Okay. Let's see if I can show you this. Right now, the TextPad editor is running in memory. And it's using up a certain amount of, it's using up, see if I go up here, I can change the columns and I can ask for the column that tells me how much memory. Oh, it's already turned on. Oh, there it is. TextPad's using 5 megabytes of memory. Okay, that's its amount of memory it's using. Well, what would happen? Okay, so that would mean that over here in this picture, TextPad is given a box that's 5 megabytes in size. Okay, now let's see if I can find something really big to open in TextPad. I have some big files. Let's see. Try to remember where I just have like a really big file I could open up. There's a 1 gigabyte file. Open it in TextPad. Okay, TextPad just opened a 1 gigabyte file. It's a zip file, so it's a binary file. But TextPad just opened a 1 gigabyte file. It can't now. Then I go over here and let's see. Huh. That makes sense. TextPad now holding a 1 gigabyte file, its memory size should have grown. Oh, I'm not sure why it didn't. I'm probably looking at the wrong column. See, TextPad needed to grow. It was holding no data. Now it's holding a massive amount of data. Okay. See, TextPad is holding a massive amount of data, so it should have grown in size. Probably, I'm not sure why it's not showing that over in Task Manager. Okay. Okay, one of the problems we want to solve is what happens when a program needs more memory. When a program dynamically needs to grow, because it, like in this case, I'm not sure what happened there, because usually we used to do, I'm not sure, if you opened a really huge file in TextPad, TextPad would need to hold more memory. TextPad would grow to hold the new data, okay? Okay, so how can programs grow? Okay, in this case here, it would grow by real easily by just changing the bounds register. If this program wanted to grow, see there's some empty space there. If this program said to the operating system, I need to grow because I want to hold more data, the operating system could say, oh, I'll change your bound register for you. Now that would have to be a system call. The base and bounds register are part of the operating system. They're part of what is, you have to be in kernel mode to change. So if this program says I need to grow so I can hold more data, this program can make a system call to the operating system saying, would you please grow my bounds so that I can hold more data? And the operating system would look to see if there's room here. Maybe it would maybe it would need to push this one down to make more room for this one to grow. But programs can grow as time goes on. Okay, and that's one of the important problems we want to be able to solve. We want the virtual memory system to be able to defragmentate memory. That's one thing we saw it can do. We want processes to be able to grow dynamically as they're running. Okay, if a process needs more memory, it should be able to request more memory. And we can do that easily by just by having the operating system change the bound register, a process can grow. And but what we can't do yet is share things. Okay, we can't have memory that's shared between two processes. That's actually one of our goals. One of our goals is to be able to share. So we want to be able to, the goals of the virtual memory system, and actually there's a section in the textbook which talks about goals. And he mentions these various goals, and they are so he had a oh, maybe it's a different chapter. He's got a section on goals that lists the different goals, and here he's got them kind of spaced out. But the goals are things like protect processes from each other, be able to defragmentate memory to make room for new processes. Eventually, we'll have a goal that, protect processes from each other. Base and bounds protects processes. That's one goal. Second goal was be able to free up memory to coalesce the fragmented memory so that we can make room for new processes. So we want to be able to defragmentate memory. So protect is goal one, defragmentate memory would be goal two. Goal three would be a process should be able to grow while it's running. If a process needs more memory at a certain point, then the process should be able to ask for more memory. So process should be able to grow. So far, base and bounds can do that goal also. A fourth goal will be you should be able to share code between processes. That we can't do with base and bounds. That's one of the limitations of base and bounds. It also, when you defragmentate, it does defragmentation slowly because you actually literally have to copy these processes and move them around. Defragmentating is inefficient. It's doable, but inefficient. So we have good protection. We have moderately good defragmentation. We have pretty good ability to grow a program. A program it's real simple, just change as long as there's space over here, you can, like this program could be slid up, and this program could be slid down, and then there'd be a lot of space here for this program to grow in. Notice that growing is a lot like defragmentating. You may have to move programs around. So programs can grow, but you have some of the same problem that defragmentating had. You have to move things around. But we can't share yet. That's going to be one of our goals, is to be able to share memory, and base and bounds doesn't share very well. Okay. So the next memory system is called segmentation. Segmentation is going to solve the sharing problem. Segmentation will look a lot like base and bounds, but it's going to be a system that's going to allow us to do, for example, to have shared code. Okay, so we're gonna in the next chapter we're gonna add to the base and bounds idea. It's not a very hard idea. We're actually going to just have multiple base and bounds. Segmentation is really just base and bounds, but you have, instead of having a base register and a bounds register, you'll have multiple base registers and multiple bounds registers. You'll have multiple pairs of these, one pair per segment. So it's actually not a complicated idea. It's a simple basis on this idea. It'll solve the sharing problem, but it won't make the defragmentation problem any better. It won't make the growing problem any better. Well, kind of, everything else will stay about the same, but the segmentation will solve the problem of being able to allow us to share memory. Two processes will be able, we could have a common C library in memory and have everybody share it with multiple base and bounds registers. Then once you have the multiple base and bounds register, it's kind of a medium-sized leap to the real virtual memory system, what's called paging. Okay, so on Monday next week, we'll do the segments. We'll do the virtual memory system that adds segments, the next chapter, which is going to be essentially this base and bounds system multiple times. Okay, we'll go from address translation, which is base and bounds, to segmentation. When you're reading it, realize he doesn't quite, well, see, generalized base and bounds. Okay, now he never draws a picture. See, he never draws a picture of the CPU. So what we're going to do is we're going to sit here and just say, okay, instead of having one base register, we have two or more base register. Instead of one bounds register, we have two or more bounds register. That's all. That'll be the change. Okay, so then we'll see that we can solve a bunch more problems then. Okay, So we can do more with that. And then though the next step after that will be the page virtual memory system. Okay. Then, but that'll be kind of a big jump, but then we'll have all the ingredients we need to see how to do things super efficiently. Okay. So we'll quit there. These pictures, you have to stare at them for a long time. Read the book carefully, add to what he has in the book. I think these pictures add to what he has in the book, but you can't do one or the other. You need both. I think his book is a good explanation, and I think it needs these pictures to make it clear. I think these pictures help his explanation, but it's not a simple topic. So you combine what he says in words with again, he only draws pictures of the virtual memory space. So combine his words with his pictures of the virtual memory space with this picture of what is inside the CPU, and I think you can get a pretty good sense of what's going on. All right, so we'll quit there, and we'll continue with this on Monday then. Anybody, any last second question? Any last second question about?
I sent you Professor Griff, I sent you an email and I was wondering if you had seen it.
Oh yeah, I'm trying to get through all my emails. It just takes me a little while to get to them. I'm sorry, but I've got so many classes and so many students. It takes time to get through the line, to move through the process. Yeah, it's just I have a lot to get through. So yeah, I
Okay.
did get the email. I'll try to answer it as soon as I can.
Okay, thank you.
Yeah, it's and that a lot of people have written to me. I'm trying to get through to answer all the emails. It just takes me a while because there really is a lot. Okay, so yeah, and same with the homework assignment. Yeah, I have to just keep going from one class. I have a lot of homework assignments to get through, and so it's taking time. Okay, so anybody, any other question? Any question about what we're doing?
Professor,
Sure.
for get current process, do you have to import a certain C library?
No, meaning for the homework assignment?
Yeah, my
No.
compiler is saying that the function's undeclared.
You need Windows.h. You have to include Windows.h, but you have to
Okay.
include that in all our homework assignments. That was included as part of the base code I gave you. It's part of Windows.h. Make
Okay.
sure you have it spelled right. Yeah, check that it's spelled right, but it's part of Windows.h.
All right. Thank you.
Yeah, all the Windows libraries, all the window libraries are part of Windows.h. So you just need that one include for everything in Windows. The C libraries is divided into a bunch of pieces. So there's a bunch of different include files for the C libraries. There's not just one of them. I think Microsoft did the right thing. They just put everything in one .h file. So you just do Windows.h and you get everything in the Windows operating system. So if it says it can't find it, it might be that you misspelled it. Look real careful, or you didn't give it the right number of parameters. Check that you have the correct number of parameters. Or send me a copy, send me a copy of the error message, and I can maybe tell you exactly what's going wrong. Okay?
All right. Thank
Okay.
you.
Other questions? Any other questions about what we're doing? Okay, so we'll meet again. Have a good weekend. See you on Monday. Bye-bye.